Okay, hopefully everybody has seen the homework, and I wondered if you've had a chance to look at it and if you have any questions.
Dr. Marks.
Yes.
So on 77, I don't know. I was confused at what E1 and E2 is. So like, is
this the a problem from the book?
yes,
Okay. Can you tell me what page it's on?
89.
Okay.
I don't know. I guess they never stated it, so I assume that we'd have to like leave them as just like arbitrary values. But
Okay.
I was kind of confused at where to start on that one.
Page 89.
Yes.
I'm sorry. I'm sure you're going to be dizzy watching this on your screens. So if you're prone to epileptic fits, I forgot the page number. 69?
89.
89. Okay. There, we're close.
And problem 77.
Okay. Problem 77. Okay, let's see. A non-symmetric binary communication channel is shown in the bottom here. Assume the input is 0 with a probability of p and 1 with a probability of 1 minus p. Find the probability that the output is 0. Well, the probability that the output is 0, the probability that the output is 0 is equal to the probability that the input is 0 and the probability that it was transmitted successfully. Now, the events of the input being 0 and 1 are mutually exclusive, aren't they? Right? So therefore, we can talk about 1 being transmitted as being mutually exclusive from transmitting 0. They're mutually exclusive events. So we can get 0 from 2 mutually exclusive events. A 0 is transmitted and a 1 is transmitted. And so therefore, yes, you go through the probability 0 was transmitted and it was transmitted correctly, or a 1 was transmitted and it was transmitted incorrectly. But I don't think that was your question. What was your question?
That's that kind of answers it a little bit, but the epsilon 1, epsilon 2 is, I guess, is that just the probability that it's transmitted incorrectly? Or what do those values represent?
Oh, the epsilon? Yes, the epsilons are the probability. So epsilon 1 is the probability that a 0 is transmitted and a 1 is received.
Okay. All right.
So 1 minus epsilon is equal to the probability that a 0 is transmitted and it was transmitted correctly.
Okay.
Does that make sense?
Yes.
Yeah, so the epsilons are probabilities, and hopefully the epsilons are what? Probability of error, correct? And hopefully your probability of error is very small, and you notice that if it's 0, you have a perfect channel with no errors at all. So does that clear that up?
Mm-hmm.
Okay. Any other questions?
On the same problem here, in the second part there, it asks which is more probable. To answer that, I think you would have to make an assumption on epsilon and epsilon 1 and 2.
Yes, you do. Yes, on part B, you have to say if epsilon 1 is greater than epsilon 2, then blah, blah, blah.
Okay.
Okay, yes, you would have to make that. Otherwise, without numerical values, you can't answer that question. Good point.
Right. Mm-hmm.
Adam, is it cold in the brick?
It is surprisingly cold here today. Yes.
Is that right? Okay, you're hooded.
Mm-hmm.
You're okay. Well, good for you. Okay, any other questions? Okay, wonderful. Then I will stop sharing the screen and get up the lectures. Let's see, I think this is the one. Yes. And I will again share the screen. I'm getting much quicker at doing this. And we will put this up. Okay. Now this is fun. I really like this. I really like this ageless exponential. This is again a model which is used extensive in reliability engineering. I started back when I got my master's degree. I worked for a terrible year and a half for the Navy. And it's not that working for the Navy is bad. It was the job I had working for the Navy was really very boring. I graduated with my master's and I thought, oh my goodness, I don't know enough to be an engineer. And I went out, and then when I got the job, I found out that I used this much of what I learned as an engineer. And it was a reliability engineer. And reliability engineers make sure that equipment, which is purchased by the DOD, the Navy, the Army, or the Air Force, lasts a sufficiently long time. So before the DOD will accept equipment manufactured by a private manufacturer, that manufacturer has to subject the equipment to reliability tests, and they usually do it in the extreme. So I would travel to places where people were trying to sell equipment to the US government, and I was the government representation for verification that this equipment worked well. So they would do things. They would put it in an oven, heat it up to 1,000 degrees, and then they would put it into a refrigerator and go down to -20, and then they'd take it out and kick it around the room and turn it on, see if it worked. So there were a battery of tests that one went through. And the interesting mathematics behind reliability is, given that something is currently working, when will it fail? What is the probability that will fail in the future? And the most common model which was used for this was the exponential random variable. And the interesting thing about the exponential random variable is that it's ageless. If something obeys a exponential random variable for reliability, that means if it works today, it's as good as new. In other words, if you have a light bulb that has been turned on, that's been working for a year, then that light bulb is as good as a brand new light bulb that you take out of the box, if it follows the exponential. And I think I mentioned last time that I am much older than most of you, but the probability that I live another day is about the same as the probability that you live another day, right? So that's kind of curious. So you didn't know it by looking at me, but I'm as good as new. if we follow this ageless exponential random variable. So let's talk about it. The probability density function for the exponential is lambda e to the lambda x. Now, x is usually measured in time. So that means that lambda has to be measured in 1 over time. And in fact, 1 over lambda is sometimes referred to as the MTBF, mean time between failures. And so if you want a good item, you want to have something which has a big mean time between failures. You want it to be a long time before your first failure occurs. Okay, so let the random variable be x, how long you've lived after you're born. We're going to look at our reliability, if you will. Thus, if we looked at the cumulative distribution function for x, we would integrate this. Remember that the derivative of the cumulative distribution function is the probability density function. So this is the corresponding cumulative distribution function, which we get by integrating this. And you've lived for y years. So therefore, we want to find out the probability that x is less than x. In other words, the probability that how long you live, given that you've lived more than y years. So this is the probability of when you're going to die, given that you've already lived for, say, 20 years. according to the exponential model. Well, if we take this first equation, and we apply the definition of conditional probability, we get this relationship. And on the next line, we know that y, which is when you're going to die, is going to be greater than how long you've lived, right? Y is going to be greater than x. So given that no, is that right? No, y is less than x. Yes, y is less than x, sorry. So y is how long you've lived. This is your age now. Because we're certain that you're not going to die because you're alive after y years. And this point is the future. And so therefore, because y is less than x, this top relationship could be the probability that your death, x is the random variable of your death, lies between how long you've lived so far and when you're going to die in the future. And then the bottom, we recognize the probability that y is greater than x is equal to 1 minus the probability that x is greater than y is 1 minus the probability it's less than y. So that's just a little bit of manipulation. Well, we know that in the cumulative distribution function, that the top is equal to the cumulative distribution function at x minus the cumulative distribution function for y. So that's what we got. You remember that if we have a cumulative distribution function, that the probability that it lies between a value of, say, y and x is equal to this distance. So if this is the random variable, the probability that it lies in this interval is equal to this result, which is the probability of the upper value minus the probability of the lower value. And this is the denominator here is 1 minus the cumulative distribution function over here. So it's e to the minus lambda y. So if we take this formula on the left, the cumulative distribution function, and we apply it to the numerator, we get this result. And you'll notice that the first term cancels the second term, and we get a distribution function of 1 minus e to the minus lambda x minus y. And that is as good as new. It might not be apparent to you, but here's what the situation is. When you're born, here's your probability distribution function, right? It's a e to the minus lambda x. What we just derived is that if you live for y years, then the distribution function of your death is exactly the same curve, except shifted to be where y starts. So that means this distribution, your outlook for the future here when you're born, is exactly the same as the outlook for the distribution after you've lived y years. Really an interesting result. So this says that you're good as new. Now, of course, this doesn't happen. This is a model, and the model isn't applicable all the time. And what happens is that there is this curve referred to as the bathtub curve. And you'll see why in a minute. And the bathtub curve goes flat for a long time. And this is a function of time. And during this period of the constant in this bathtub curve, your probability of living is exactly the same thing. But on the one side is exactly the same probability, but on one side is something called infant mortality. And you know why that is, because many times when babies are born, they don't live very long. And on the other side is old age. In fact, when I was a reliability engineer for the Navy, I went to one place and they said, okay, you ready? I said, yep, I'm here for the United States government. I'm going to watch you put this equipment on test. And they turned the thing on and it lasted for about 2 seconds and they failed. And they said, wait a minute, we didn't have the startup right. Just let us start over again. I couldn't do it. I said, this was an example of infant mortality, right? That you don't have these new things. And of course, as you get older, there is old age. But in this region here, when it's flat, then you are as good as I am, and as far as living for maybe another day or so. Indeed, you're probably familiar with, I don't know if they still do this, but they used to, for integrated circuits, they used to turn them on and have a burn-in time where they let the circuits operate for a while to weed out all of the infant mortalities. And sometimes the government would require this for the delivery of IC chips and things of that sort. Okay, so this is the exponential. We're kind of reviewing here, by the way, the different probability models, probability density functions, and I'm trying to give you a little tease as to where they are used. We'll also find out that this exponential random variable is applicable in other places. Here is a Cauchy random variable. Now, the Cauchy random variable is a very interesting random variable. In fact, it's the bad guy of random variables. And I will tell you why it's a bad guy of random variables. By the way, I make my A's 2 different ways, and I've given up trying to be consistent. The Cauchy random variable kind of looks like a bell-shaped random variable. It's kind of centered at A, but it's a bad boy. And it's a bad boy in the sense that its mean is undefined, and we'll find out why the mean is undefined. And its second moment, and therefore you could argue its variance, that is how much it is spread out, is infinite. And it's just a weird random variable. However, it is not it is not something which is made up by mathematicians to be weird. One of the places where the Cauchy random variable occurs is in the so-called loose cannon random variable. And here's the idea. You have a little cannon here. And this cannon is chosen with a random variable of theta, where theta goes between 0 and pi. Is that okay? So you choose a random angle between 0 and pi. And then you put a wall up here. And you shoot at this wall. We will show this later. Now, this is going to be a random variable x up here. Where it hits the wall is going to be a random variable x. So we choose a cannon. We choose a cannon at a arbitrary angle, and we shoot at a wall. And wherever it hits the wall, this is the x is equal to 0 now. Wherever we hit the wall is a new random variable x. It turns out that in this loose cannon case that, yeah, it turns out that the random variable x is a Cauchy random variable. And Cauchy random variables pop up in a number of places. And it looks kind of innocent, but it has problems. One of the problems is it has fat tails. And that is, if you go to infinity, what does this go to? This goes to 1 over pi, 1 over x squared. Right? So as x goes to infinity here, this distribution goes to 1 over pi, 1 over x squared, right? It totally swamps the value of b, totally swamps the value of a, and it's just 1 over x squared. So it goes down as a 1 over x squared, which is a very, very slow descent. Now, even though this is a innocent appearing random variable, it's dangerous. We'll appeal to it a lot. It's kind of the bad boy. that we will talk about, but there's also random variables which are even worse than the Cauchy. One of them is the Pareto random variable, which we'll talk about in a little bit. This is Cauchy. He was born in Paris, and he was a French guy, and he was a Christian, as you can see on the bottom left. This is what a Cauchy looks like for centered at the origin. And again, it looks like, you'd look at this and you say, oh, it's kind of like a Gaussian. No, it's very, very different from a Gaussian because it has very, very fat tails. Here's a Laplace random variable. Laplace was a really smart guy. He was in France, and he was one of the guys that helped found the metric system. And he was just a brilliant, brilliant man. And the Laplace random variable is, as you can see here, a over 2 e to the minus ax. So therefore, it's a double-sided sort of probability density function that looks like this, with a cusp in the middle. So that was Laplace. Laplace was, he has a bunch of namesakes. You've all heard of the Laplace transform, Laplace noise. And we talk a lot about some of these different mathematicians and such being Christians. Laplace was an outspoken atheist. When he submitted his thesis on celestial science to Napoleon, Napoleon leafed through it and he says, you know, I see no reference here to God. And Laplace famously replied, sire, I had no need of that hypothesis. So he was an atheist. And you're all familiar with the Laplacian operator, I hope, in electromagnetics. You've all seen this. Yeah, so therefore he's, we will talk about Laplace noise, and everybody who's an electrical engineer has heard of the Laplace transform, because it's very useful in solving circuit problems and linear time invariant differential equations. Here's the gamma random variable. On the upper right, you can see a picture of Vasco da Gama. And you can read this. He has absolutely nothing to do with the gamma random variable. Okay, this is my joke. Okay, it's a joke. Because
for me, it's fine. For me.
Oh, okay, it's okay. It's hard to make jokes when you hear no response. So I saw a couple smiles. Yeah, the gamma random variable, of course, is named after the third letter in the alphabet, alpha, beta, gamma, and is given by this distribution. I wonder if da Gama, though, this has any relationship with the third letter of the alphabet. Glauco
I don't think so. I don't think so.
You think it's just a coincidence, huh?
Yeah, I think the origin is different.
Okay. I want to see something here. Okay. What is the gamma random variable? If you took multidimensional signal processing, you know about this. Suppose that we had n, and we looked at n factorial. So we're going to do a plot of n minus 1 factorial. So 0 factorial is 1, right? And if n is equal to 2, 1 factorial is also 1, right? 2 factorial, 3 corresponds to 2 factorial, which is 2. And 3 factorial is 6. So we know that the gamma function really goes up quickly. Or we know that the factorial function goes up very quickly. What the gamma function does is it allows a nice curve which goes through all of these points. And so the gamma function is kind of the generalization of the factorial for all of these different points. It turns out that the gamma random variable has a number of special cases, which we find very, very useful. And so all of these random variables, as you notice, are parameterized by different things. different numbers. So when we talk about a specific random variable, we're literally talking about a family of random variables. You can see here that we have A as a parameter, we have lambda as a parameter. So there's two parameters to the gamma random variable, and depending on what it is, it can take on various shapes. If you look at, I don't know, MATLAB or probably even Excel, you can probably get values of the gamma function just by writing like you can for the sine and cosine. And so you can get gamma functions. And as you can see that the gamma of n, as we see down here, that the gamma of n is equal to n minus 1 factorial. So that's the gamma random variable. And again, in general, I don't know, it's not too impressive, but we'll look at some special cases of this later. There's a Weibull random variable used quite a bit, actually used in reliability, the sum. It's kind of a generalization of the exponential, and it has two parameters. It has a lambda and an a. And you can see for a is equal to 1, it's just a lambda e to the minus lambda x. So for a is equal to 1, the Weibull random variable is equivalent to the exponential random variable. Everybody who's taken statistics is familiar with the chi-squared random variable, correct? You use this in statistical testing and things of that sort. Here's the probability density function for the chi-squared random variable. It also involves a two parameters. No, I guess just one parameter, a, and that usually is referred to what is the degrees of freedom of the chi-squared random variable. And this is a special case of the gamma random variable. It is a special case of the gamma random variable. And here's some other ones. There is the F distribution. They use this, and you've probably used this if you've taken a course in statistics for engineers where they teach you about different tests for hypotheses and things of that sort. And that's the F random variable. You can see there's a lot of gamma functions in here. And the student T distribution is down here. Anybody know what the student T distribution is that they teach you about in courses like statistics for engineers? It's the distribution when you have a low number of samples from a Gaussian distribution. And the cool part about this is the history. The student's T was discovered by this guy here, William Seeley Gossett. And he worked in England, and he was an employee of the Guinness Brewing Company. And he was in charge of, the statistics and the accounting and all of the other stuff. And he came up with this result. But the idea that people in industry should do research is a newer idea. And he did not want Guinness to find out he was dinking around with probability. This is even true in academia. It used to be the philosopher Popper, for example, talks about when he was working and he was publishing, and his university didn't like him to publish because they thought it was taking a time away from his students. They said, don't do that. Spend your time teaching students. And it was the same thing with Gossett working for the Guinness Brewing Company. They say, don't spend your time doing all of this mathematics. Spend your time making better beer. So Gossett, he decided his result was important, and it is important. So he decided that he was going to publish this, and he published it under the name Student T. And that was his pseudonym to hide his identity when he published this result. And the result of that is, even today we hear of this referred to as the student T distribution. Here's some other ones. A Rice random variable. This involves a Yeah, these density functions can get pretty crazy. This involves a modified Bessel function, but is very important in areas such as radar, the Raleigh distribution function. And here's the really, really weird one. This is the Pareto random variable. The Pareto random variable is really, really weird. It's if you take the log of both sides, you get something like what, minus the log of, whoa, what happened to my pen there? Okay, my pen is not allowing me to erase. I'm sure I could, but this would be something like minus the log of, well, let's see. Man, I'm having a hard time here. Let me do this and pop it up again. That's the only way I know how to do this erasure right now. Grab my pen so that I don't look at this. So the log of f sub x of x is equal to, the most important part is a plus 1 times the log of x, right? And then it's plus some other stuff. This is the only functional part of it, right? The log of x. Do you see that? So if one is to plot this as a function of x, if you plot the log of f sub x with respect to x, you get a straight line which goes down. And it has a slope of what is it, minus a plus 1. That's the slope of it. This is something called a power curve. And it says lots of things are populated here, but only a few things are populated here. And this power curve has application in a number of places. There is this book referred to as Ubiquity, which goes all over the places where the power curve is used. I'll give you an example. One is income. Okay, probably you as graduate students are right in here. I, as a old professor, am probably right in here. And Bill Gates and Elon Musk are way up here. Very small number of occurrences, right? The other one is size of cities. We have just a few city sizes. We have a lot of things like Waco, which is around 100,000 or so. But then there are up here, there are the Houstons and the Tokyos and things of that sort. So the size of cities obeys a power curve, at least in terms of the model. Another interesting one is avalanches. And I don't know how to spell avalanches, so I just put AV here. But if you look at the mountain and snow coming down, there are little things where something happens and a snowflake falls and 3 or 4 snowflakes or 3 or 4 pieces of snow, whatever a piece of snow is, goes down the mountain. But then every once in a while, boom, you get these incredibly large avalanches up here. So avalanches follow the Pareto curve, which is again called a power curve. So it's a very interesting technique. And Pareto was I believe he was an economist, and he came up with this to describe a number of the phenomena. One of the interesting things about the Pareto curve is for certain values of A and B, and you can see the parameters here are A and B. For certain powers of A and B, not only does the Pareto have an infinite variance, but it has an infinite mean. Wow, which is really, really strange. And so Pareto, we talked about Cauchy being a weird bad boy. The Pareto is even weirder and badder. And we'll talk about that later. We haven't talked about moments yet, but it's just a strange random variable. Now, there are also mixed random variables. We've talked about discrete random variables such as the binomial, the Poisson, and we've talked about continuous random variables like the Cauchy, like the Gaussian, like the Pareto random variable, where they're continuous. There are also mixed random variables, and the one that I like to use and give as an example is the is a traffic light, which you can see here at the right. And I'm sorry I put this animated GIF here because it's really bothering me now because it's flashing and taking my attention. Okay, but here's the problem. A traffic light is red 3 minutes and then green 2 minutes. Is that okay? Now you come to this traffic light and let T be the time you need to wait for the light. Now, if you arrive at an arbitrary time, the time that you wait for the light can be 0, can't it? Because you just go straight through. If you arrive when the light is red, you have to wait for a certain amount of time, depending on how much time is already lapsed for the red light. So that turns out to be a continuous portion. So we have mixtures of both. We have a discrete component, we have a continuous component. And the reason that I like using Dirac deltas instead of discrete random variables is because this allows us to be very nice. So here is the cumulative distribution function. The cumulative distribution function is, as you can see here, that's the probability that the time is less than or equal to t. Well, since the traffic light is on for 2 minutes, the green light is on for 2 minutes, and the red light is on for 3 minutes, your probability of 0, of not waiting at the light at all is 2/3 or 2/5, I'm sorry. Because the period of the traffic light is 5 minutes and you have 2 of those minutes where the light is green. The rest of it depends on where you where you arrive, and that's a continuous random variable. So this is the cumulative random variable, which describes of this 2 minute, 3 minute, 2 minute on green, 3 minute on red traffic light. Now we get the distribution of this by a derivative. And this derivative, what is this derivative going to be? What happens if we were to try to compute f sub t of t, which is the derivative of the cumulative distribution function? Well, in order to differentiate here, we have the derivative of a discontinuity. I think a mathematician would say that the derivative is not defined yet there. We know different as engineers and physicists. We know that the derivative of a discontinuity is a Dirac delta, and the weight of the derivative, or the weight of the Dirac delta, is equal to whatever the discontinuity is. So we have a Dirac delta here at the origin if we do the derivative. So it's going to be 2/5 times the Dirac delta located at the, well, where'd it go? Where'd all my beautiful artwork go? Okay, got to do it again. Someday I will be the master of this pen. That day has not arrived, but someday I guarantee it. So the Dirac delta at the origin would be equal to 2/5. Why the 2/5? Because this interval is 2/5. It's 2/5 times the Dirac delta at the origin. Then the rest of this is going to be what? It's going to be the derivative of a line, which is a constant, and that constant is always going to be the slope. What is the slope? The slope is the rise over the run, which in this case is 3/5. which is equal to 3/5. That's the rise over the run, which is 3. So it looks like it's going to be 1/5, correct? And that's going to be between 0 and 3. Right, derivative is equal to rise over run. So that's equal to 1/5. Now, does this thing have an area of 1? What's the area here? Under that rectangle is equal to 3/5, right? The area under the rectangle. The area under the delta function is 2/5. So yeah, it does add up. The area under the distribution is indeed equal to 1. The area under the density function, which indeed it always has to be. And you can see the cumulative distribution function on the left is monotonically increasing. So it fits all of the criteria for a cumulative distribution function. So this is the example of a traffic light where the random variable is mixed. You have a little bit of discrete, you have a little bit of continuous, and these happen occasionally. And the beautiful thing again about putting in the Dirac delta is that we are allowed to treat this as a single case. It's not discrete, it's not continuous in the classical sense. It has components of both. And using the Dirac delta allows us to make that relationship nicely and without any ambiguity or anything else. Any other problems? Okay, so any questions on this material at all? Again, I'm hoping that it's relatively old to you and that this is a review. You might have seen some distributions which you weren't aware of, but hopefully they fit in the context of what you've learned before. So having no questions, let's move on to something else, and that's information and entropy. Probability was, in 1948, discovered to be incredibly important to communications. And there was a guy named Claude Shannon who published a wonderful paper in 1948. He was working for the Bell Bell Laboratory, Bell Labs, and he published this paper, and it was such a beautifully written, complete paper that today in courses on information theory, the first few weeks is dedicated to coverage of Shannon's original work. But his ideas relate to probability. There is a course which I teach called Introduction to Information Theory, which goes into this more deeply. But I wanted to give you kind of a hint of the applications of probability to information theory. So let's take a look here. Information theory and probability. Shannon was saying, what was information? It turns out that if you talk about the definition of information, it depends on the field you're in. Physicists would say all information is physical because they think information has to do with the existence of wave functions. There's another theory called Kolmogorov information theory, totally different than Shannon information theory, and that's a different view of probability, or a different view of information. And so everybody can have different views of information. And I start off the course by asking questions such as, we all agree that there's information in a book, right? Right, if I have a book here, how about that? I have my, this is the text we used for it, Elements of Information. So this is a nice thick book. If I took this and I ran it through a shredder, would I be destroying information? Well, what about if there's another copy of it somewhere?
Here, there is another copy here.
It's another copy. Okay. Everybody put up their Introduction to Information Theory books. Okay.
I got the PDF, so I got as many copies as you want.
Okay. Okay. So anyway, so there isn't an answer to it. It depends on how you define information. If I take my camera here and I take a selfie, you know that when I take a selfie, I make a image of a few, I don't know, a million bits or bytes or something like that. Am I creating information when I do that? It depends on your definition of information, so you have to be careful. So Shannon was interested in the definition of information related to communication. And he thought a little bit and he says, what does information tell us in general? Well, one of the things he thought was small probability events should have more information than large probability. So if you say somebody is a nice person, well, that's very general, not a lot of information there. If you're saying somebody is a philanthropist, that's less used. That description is less used, so you would have more information. So small probability events should have more information than large probabilities. The other thing is that information from two disjoint events should add. If I say the word engineer and it has information I1, and I say stuttering, which might have information I2, if the two are unrelated to each other, stuttering engineer should add information I1 plus I2. So we would like information to add. Does that make sense? Now, the idea of stuttering and engineer have to be disjoint. If I say a hopping kangaroo, that's kind of redundant, right? Because all kangaroos hop. So hopping kangaroo would not obey this I1 plus I2. But if they are independent events, independent concepts, they should add. So let's keep that in mind. These are the axioms we would like to apply. Small probability events should have more information than large probabilities. If I tell you that the sun is coming up tomorrow, I'm not telling you much information. If I say that the sun is going to go supernova tomorrow, whoa, that's a low probability event. That is something which is going to have a large probability. Well, Shannon showed that there was only one function that described all of this, and this is minus the log of the probability. So you can see here that the minus the log of the probability, as you can see in this curve here, as the probability goes from 0 to 1, obeys the idea that small probabilities will have really big information. Where, I'm sorry, let's see, how did I say that? Yeah, small probabilities have big information, whereas big probabilities have small information. So it obeys that. So it obeys that first axiom, right? It obeys that small probability events should have more information than large probabilities. So it obeys the first axiom here. What about the second axiom? Information should add. And we'll see here the necessity of independent events. Well, before we do that, let's talk about the units. Shannon showed that it was the logarithm, but we really haven't specified what the base of the logarithm is. We'll be using base 2 because if we do base 2, then I is measured in bits. If we use 2, information is measured in bits. But there's also other things. There's the log base 2, which is bits. If you take the log base E, information is referred to as naps. So you didn't know that you can take 20 bits and make it into so many naps. And log base 10 is a Ban or a Hartley. Hartley was also a genius that worked at Bell Labs also. Okay, well, I guess I didn't put it in here. Let me do this. So we have P1. I wanted to show the second axiom was true. This is, for example, the information from stuttering. I2 would be the information from being an engineer. What is the probability of being a stuttering engineer? It is P1 times P2, right? Since they're independent events. But that's equal to minus the log of P1 minus the log of P2. which is equal to I1 plus I2. So if we have independent events, the information from the independent events adds. So we've established that the second axiom is true. Kind of cool. Now let's apply this to something we know, which is bits. Suppose we flip a coin 10 times. What is the probability that we come up with this exact sequence? Tails gives us a 0, heads gives us a 1. So we get tails, tails, heads, heads, tails, heads, 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 tails, heads. The probability of coming up with that exact sequence is the probability of the first event times the probability of the second event, etc. So each one of the probabilities is 1/2. So it's 1/2 raised to the 10th power, since there's 10 bits here. That would be the probability of getting this exact sequence of ones and zeros, correct? We can also plug this into the definition of information and talk about the information with it. And it would be the information for these 10 bits would be equal to minus log of 1/2 to the 10th, which is this probability. Hey, and it's 10 bits. So we get the idea of how we relate probability to bits here, which is really, really nice. One of the cool things about this is I like talking in terms of probability in bits. You can make a transformation between probability and bits. You can talk about, for example, a probability of 1 billion. 1 chance in 1 billion. I don't know what that is. One chance in 1 billion, 1 chance in a 10 billion. I know what the numbers are for, but I do not have an intuitive grasp of what 1 chance in 1 billion is. However, 1 billion is about equal to 2 to the 30th, roughly. If you think about it, what is 10 bits equal to? That's 2 to the 10th is about 1,000. So 2 to the 20th is about 1 million. 2 to the 30th is about equal to 1 billion, roughly. So what does this say? This says this probability translates to I is equal to 30 bits. Right? So we can interchange between probabilities and bits. This is a different way of thinking about it, I'm sure, than you've thought about it before. But a probability of 1 in 1 billion is about the same as me flipping a coin 30 times and getting 30 heads in a row. It's about the same as me flipping a coin and getting 30 heads in a row. And that, to me, is more intuitive than 1 chance in 1 billion. I can understand a little bit better flipping a coin and getting 30 heads in a row. I mean, that's a lot of heads, but that is much more intuitive to me than 1 chance out of 1 billion. The other cool thing is the application of this to 20 questions. If you've ever played the game of 20 questions, you have a chance of telling people, you have a chance of querying somebody to identify what they have in mind. And we're going to see that this information applies here. Say, for example, we have 16 squares. So we have 16 squares here. And I choose 1 square. And you have to guess what that square is by asking me yes or no questions. You have to guess what that square is by asking me yes or no questions. It turns out that the information associated with 1 and 16, which is 4 bits, is the number of questions which you have to ask me. That's the minimum number of questions there's many ways to ask questions, but if you ask them the right way, you will only require 4 bits of information. So you will ask me one question and I will say no. You have a 0. You ask me another question. Yes, I get a 1. You ask me another question. I say no, it's a 0. I ask a third question. I get a 0, no, which is a 0. So by 4 bits of information, I should be able to identify this. It isn't apparent without me elaborating, but that's indeed the case. Let's indeed do this. Let's number the squares. I think I do this in the future. I should have looked at this more closely. Well, okay, this is okay. I did it totally wrong. Daggone it. Oh, well, let's see. Let me just do this. What I should do, I'm not thinking appropriately here. This should be 0, 1, 2, 3, 4. In other words, I want to start at 0. And the way you ask the questions is by interval halving. And we should be able to identify it within 4 questions. So the first thing you do is you say, is it a number between 8 and 15? And I would say no, right? Is it a number between 8 and 15? That would be my first question to you. You would say no. A no is a 0. Then I would know that none of these numbers are the answer. Then I would ask, is it a number between 4 and 7? You would answer yes. And when you answered yes there, that would eliminate all of these possibilities. Right? Then I would ask, is it a number between 5 and 6 and 7? I know it's one of these 4 numbers here. Is it a number between 6 and 7? No, it isn't. So I know it isn't this. So now I know I've narrowed it down. It's either 4 or 5, right? So I say, is it a 5? And we say, yeah, it's a 5. So that's a 1. And I have identified it in 4 questions. Not only that, watch this. This is cool. If you look at my answers and look at a base 2, what's the answer? 5. So not only that, I'm able to identify the number just by the yes and no questions by the binary 10101. And you got to be impressed with that. So that's another example of the application of information, is it tells us how much information do we need in order to differentiate one number out of 16. And this is really kind of cool because we said 2 to the 30th is about 1 billion. So if I gave you 1 billion squares, you could narrow it down to the 1 square in about 30 yes and no questions. If I had 1 billion squares, interval halving is very powerful, as you can see. But the point here is that Shannon's measure of information tells us how many guesses that we are going to need on optimally in order to choose the right result. The most fundamental idea of information is a Bernoulli parameter. You remember Bernoulli trial, it gives you an output of either a 1 or a 0. And it has a success with a probability of P. So the information from a success is the log of P. So if you get a success, this is how much information you get, right? If you get information from a failure, that's log of 1 minus P. It's always minus the log of the probability. If you do the average, you will get this much information P% of the time, and you will get this much information 1 minus P of the time. And average information, as we do here, is referred to as entropy. So we get this P% of the time. We get this amount of information 1 minus P% of the time. So this is the average information. So if we have a trial and we have a number of outcomes, each one of those outcomes gives us a different probability, right? Now, all the probabilities, because they're mutually exclusive and exhaustive, have to add up to 1. But each one of the outcomes gives us a different amount of information. We want to look at that experiment and the average information that we generate. And this is this H is probably the most simple of the average information. And if we plot it, it looks like this. And this is referred to as H of P. So it's a number which goes from 0 to 1, depending on the success of your Bernoulli trial. When do you get the most information on average? On average, you get the most information for P is equal to 1/2. So a fair coin will give you the most average information. What if your probability of success was 0? Well, if your probability of success is 0, that's not very exciting, right? If you always get the same answer all the time, that's no information at all. So we might expect that we have an average information of 0 because it's always the same. The same on the other end. So this is the binary entropy function. And so this is the general definition of entropy. The idea is you have an outcome and you have different chances of this outcome. And we can look at a Venn diagram. And this is the probability 1, probability of 2, probability of 3, probability of 4. Let's even put, and probability of 5. And let's even put this in. Probability of 6. Okay. So the point is we have all these probabilities and all these probabilities add up to 1. So with the Bernoulli trial, there's only 2 partitions. There's P1 and P2, success or failure. Here we have a number of them. This is like a loaded die. Remember, you can have 6 outcomes possibly. And so we're saying that these probabilities are different for each outcome. So the total amount of information for each one is minus the log of P sub n. So the information corresponding to this outcome is minus the log of P sub 6. And if we average all these together, we're going to get this. This is the average information. This is referred to as entropy. You are familiar with the idea of entropy from thermodynamics, and there is a relationship. And maybe if we have time, we'll talk about that a little bit. We do in the course on information theory, if you're interested in it. Okay, here is the entropy of uniform distribution. Uniform distribution is equal to 1 over k. So it looks like this for a discrete distribution. And if there's k values and each one is equally probable, then each one of them has a probability of 1 over k. So the probability of each one is 1 over k. And then if we perform this summation, we get the summation of k is equal to 1 to k of the probability times the log 2 of the probability. Notice that this is something which, well, here's an old question. What is the summation of n is equal to 1 to 3 of 2? It's one of these degenerate cases that is so simple. You look at it and you go, I'm not really sure what that is. Well, what is it for n is equal to 1? It's equal to 2. What is it for n is equal to 2? It's equal to 2, 3. So it's equal to 6, right? So that's what we have here. We have the case of lowercase k, but notice nothing in here. Nothing in here is a function of little k, is it? Nothing in here is a function of little k. So this is exactly like 1 over k times the log base 2 of 1 over k times the summation of k is equal to 1 to big K of 1. Okay. Because we can suck all of that stuff outside the integral. And I guess there's a minus here too. This summation, of course, is equal to K. And what we're left with then is the log base 2 of K. So that is the entropy of a uniform random variable. Well, we haven't talked about expected values, so I'm going to skip this. Here's a geometric random variable, and this geometrical random variable, we remember you apply a Bernoulli trial till you get a success. So you want to roll a die until you get 6 pips. And so the probability of success there is 1/6, and this was the geometric random variable. This is the probability mass function for rolling the die before you get your first 6. If you were to apply the entropy equation to this probability density function, Q here, by the way, is equal to 1 minus P. That's a common substitution. You come down, it's equal to H sub P over P. Now, what is H sub P? Well, interesting. H sub P is this function that we derived way back here. This is H sub P. Remember H sub P? It's a little H sub P. So if we did the repeated Bernoulli trial, if you go through the math, it turns out to be exactly that same function divided by P. So it turns out the average information for when P is equal to 0.5, in other words, you flip a coin, a fair coin until you get a heads, is 2 bits. That's the average information that you get out of that result. Well, I think we've probably come up to the point where it's time for us to leave. Our time has run out. Next time we'll stop here and we'll show some interesting things about entropy, and we will show another very nice applicable application. That's redundant, right? We'll show another application of entropy where it does some really cool stuff. So the next time we meet, we'll probably go into the solution of the homework problems, and I'll choose you guys at random and let you dazzle us. So be prepared to display your results either through an electronic means or through camera, if you have a camera that you can focus on your thing. I bought me one of these little overhead cameras a while back, and you know what? I've never had the time to set it up. It's one of these, okay? You know, it has a little arm that comes out and you put your document under it. So if you have one of those, I know one student had one of those last time. Okay, any questions at all? Okay, thank you very much. So until next time, be of good cheer.